Now, let's recall that in pure water, concentration of protons is 10 to the negative 7 molar. So, what does it mean for us from practical point of view? Concentrations of acids or bases below 10 to the negative 8 will not affect pH value. Why? Because these concentrations are too small comparative to 10 to the negative 7 you already have in water. Concentrations between 10 to the negative 6 and 10 to the negative 8 require special treatment. In practice, this will be affected mostly by CO2 and ammonia from air. So only concentrations above 10 to the negative 6 molar may change the pH value of solutions in water, and only in absence of other acids and bases. So conclusion: very small concentrations do not change pH at all. If you are adding molarity below 10 to the negative 8, nothing happens. Look at this chart. You have linear dependence of pH from log of concentration both for base and for acid, but below 10 to the negative 8 you have pH 7, which is pH of neutral solution. Now, dissociated constant of conjugated acids and bases are related. Let's consider this reaction. Acid, NH4+, dissociates into base and hydrogen ion. The equilibrium constant Ka will be H plus A for an ion and HA for acid. So reaction is HA makes A base and H plus. Next, for the same equilibrium, we can rewrite it from right to left, so opposite reaction. Base, ammonia, reacts with water to make NH4 plus acid, same acid as here, same base as here, and hydroxide ion. Kb will be, as usual, acid concentration, hydroxide concentration, and base concentration. Equation is A plus H2O, HA plus OH minus. Now, these two constants describe essentially the same process. This is forward reaction, this is reverse reaction, so they must be related. Let's add these two equations. So base equation adding to acid equation algebraically. What we'll have? Okay, HA at the left side, HA at the right side, A at the right side, A at the left side. So we have H2O dissociates into H plus and OH minus. Now, this is familiar self-ionization or auto-ionization of water. And we know this constant, it's Kw. Now, what about constants? We can multiply Ka by Kb algebraically. What will happen? So taking this expression, multiplying by this expression. Above the line we have A, below the line we have A again. Above the line we have HA and HA below the line. So they will cancel. What's left? H plus and OH minus. Now we know this product, it's Kw. So Ka multiplied by Kb is Kw, and it is equal to 10 to the negative 14. Now if we'll take log of this, we'll have pKa plus pKb equal to 14. Now that means if you know pKa, you can calculate pKb. If you know pKb, you can calculate pKa. Next, when you dilute solution of weak acid, the fraction of dissociation increases. Eventually, it may start behaving like strong acids. See at this figure. Salicylic acid, great line, is very weak at 0.1 molar concentration here. It's only 10% dissociated. But when we are going to diluted solution, 10 to the negative 4, it's essentially strong. It dissociated by 95%. This same effect is true for parahydroxybenzoic acid. It's very weak at 0.1 molar solution, couple of percent dissociation. Same 10 to the negative 2, same 10 to the negative 3, and even at 10 to the negative 4, it's still weak. But at 10 to the negative 6, it is essentially strong. Any acid is strong at very low concentration. But it doesn't change the pH, because if you have 10 to the negative 6 molarity, that means concentration of protons you are adding is still very small. It's even less than 10 to the negative 6. So how we calculate pH values of solutions? Strong acid. Very simple formula. pH is negative log of total molarity of acid solution. Why it is so? Because all molecules of acids are making equivalent number of protons. So total concentration of proton is equal to starting molarity. For example, let's calculate pH of 0.01 molar HBr. HBr is a strong acid. pH will be equal to negative log of concentration, so negative log of 0.01. 0.01 is the same as 10 to the negative 2, so decimal log will be minus 2 with negative sign here. pH will be plus 2. So we are just hooking the number in a formula, putting minus before, and do the calculations. Exactly the same formula is true for hydroxide, for bases. So POH will be negative log of concentration of C. Now we remember that pH is 14 minus POH, so we can rearrange the formula to make pH equals to 14 plus log of concentration C, where C is molarity of the base. So let's calculate pH of 0.001 molar sodium hydroxide. Sodium hydroxide is a strong base, so this concentration is essentially concentration of hydroxide ion. So hooking numbers in a formula, pH is 14 plus log of 0.001. This log is minus 3. So total is 14 minus 3. pH is 11. Now, let's double check. This pH is much less than 7. It's acidic. We did not make a mistake. This pH is much higher than 7, so it's strongly basic. So we did not make any errors. One more example. Let's calculate pH of 10 to the negative 9 molar sodium hydroxide. Okay, we recall that concentration is smaller than 10 to the negative 8 molar. Therefore, no change of pH. Amount of sodium hydroxide is too small to affect pH of aqueous solution. We have just plain water, and pH is still 7, as it was.